Good morning. Today we are going to talk about measurements and experimentation. The topics covered in the lesson are need of unit for measurement, systems of unit, units of length, units of mass, units of time, some examples of derived guidelines for writing the units. Systems of unit and units in SI system. Need of unit for measurement. Physics, like other branches of science, requires experimental studies which involve measurements. For the measurement of a physical quantity, we consider a constant quantity of same nature as a standard, and then we compare the given quantity with the standard quantity. That is, we find the number which expresses how many times the standard quantity is contained in the given physical quantity. Thus, measurement is the process of comparison of the given physical quantity with the known standard quantity of the same nature. The standard quantity used to measure and express the given physical quantity is called the unit. For the quantities of different nature, we require different units. Unit is a quantity of constant magnitude which is used to measure the magnitudes of other quantities of the same nature. The result of measurement of a given physical quantity is expressed in terms of following two parameters: the unit in which the quantity is being measured and the numerical value which expresses how many times the above selected unit is contained in the given quantity. Thus, the magnitude of physical quantity is expressed as physical quantity is equals to numerical value into unit. Choice of unit. Since a unit is to be used universally, it should have validity everywhere at all times. Hence, to measure a physical quantity, the unit chosen should have the following properties. The unit should be of convenient size. It should be possible to define the unit without any ambiguity. The unit should be reproducible. The value of unit should not change with space and time. That is, it must always remain same everywhere. The last three conditions are essential for a unit to be accepted internationally. Let's see the kind of units. Units are of two kinds: fundamental or basic units and derived units. Fundamental or basic units. A fundamental or basic unit is that which is independent of any other unit or which can neither be changed nor can be related to any other fundamental unit. Examples: the units of mass, length, time, temperature, current, and amount of substance are independent of each other. As they are of different nature, they cannot be obtained from the unit of any other quantity. These are fundamental units. Derived units. Derived units are those which depend on the fundamental units or which can be expressed in terms of fundamental units. Examples: for the measurement of area, we need to measure length and breadth in the unit of length and then express area in a unit which is length into length or length square. Volume is expressed in a unit which is length into length into length or length cube. The unit of speed of a moving body is obtained by dividing the unit of distance, that is length, by the unit of time. That is, it can be expressed in terms of units of length and time. Thus, the units used to measure area, volume, speed, etc. are derived units. Systems of unit. In mechanics, length, mass, and time are three fundamental quantities. For the units of these three basic quantities, following systems have been used. CGS system or French system. In this system, the unit of length is centimeter, which is cm, of mass is gram and is denoted by g, and of time is second, which is denoted by s. The second one is FPS system or the British system. In this system, the unit of length is foot, which is ft, of mass is pound and is denoted by lb, and of time is second, which is denoted by s. MKS system or the metric system. In this system, the unit of length is meter, which is denoted by m, and of mass is kilogram, which is denoted by kg, and time is second, which is denoted by s. The above mentioned systems are now no longer in use and are only for historical importance. For the sake of uniformity, the scientific community has agreed to use the SI system of units, which is an enlarged and modified version of metric system. System International Units or SI system. In 1960, the General Conference of Weights and Measures recommended that in addition to the units of length, mass and time, the units of temperature, luminous intensity, current and the amount of substance also taken as fundamental units, and the units of angle and solid angle are complementary fundamental units. Thus, in all, now there are 7 fundamental units and 2 complementary fundamental units. Fundamental quantities, units and symbols in SI system. Let's go through a detailed table of quantity units and their symbols. Length, meter, m. Mass, kilogram, kg. Time, second, s. Temperature, Kelvin, K. Luminous intensity, candela, CD. Electric current, ampere, A. Amount of substance, mole, MOL. Angle, radian, RD. Solid angle, steradian, ST-RD. Use of prefix with a unit. For expressing large measurements, we use deca, hecto, kilo, etc. as prefixes with the units. The symbol and meaning of each prefix are given below. Some prefixes used for bigger measurements. Prefix, symbol and meaning. Deca, the symbol is DA, meaning 10 to the power of 1. Hecto, H, 10 to the power of 2. Kilo, K, 10 to the power of 3. Mega, M, 10 to the power of 6. Giga, G, 10 to the power of 9. Tera, T, 10 to the power of 12. Peta, P, 10 to the power of 15. Exa, E, 10 to the power of 18. Zeta, Z, 10 to the power of 21. Iota, Y, 10 to the power of 24. The various small measurements are expressed by using the prefixes deci, centi, milli, micro, etc. with the units. The symbol and meaning of each such prefix are given below. Some prefixes used for small measurements. Prefix, symbol and meaning. Deci, D, 10 to the power of minus 1. Centi, C, 10 to the power of minus 2. Milli, M, 10 to the power of minus 3. Micro, mu, 10 to the power of minus 6. Nano, N, 10 to the power of minus 9. Pico, P, 10 to the power of minus 12. Femto, F, 10 to the power of minus 15. Atto, A, 10 to the power of minus 18. Zepto, Z, 10 to the power of minus 21. Yoito, Y, 10 to the power of minus 24. Units of length. The SI unit of length is meter, which is denoted by letter M. A meter was originally defined in 1889 as the distance between two marks drawn on a platinum iridium, an alloy with 90% platinum and 10% iridium rod kept at 0 degrees Celsius in International Bureau of Weights and Measures at Sèvres near Paris. In 1983, the meter was redefined in the terms of speed of light, according to which 1 meter is the distance traveled by light in 1 by 299,792,458 of a second in air or vacuum. Subunits of a meter: centimeter, millimeter, micron, and nanometer. 1 centimeter is equals to 1 by 100 meter, which is equals to 10 to the power of minus 2 m. 1 millimeter is equals to 1 by 1000 meter is equals to 10 to the power of minus 3 m, which in turn equals to 1 by 10 centimeters. 1 micron or mu is equals to 10 to the power of minus 6 meter is equals to 10 to the power of minus 4 centimeters, which equals to 10 to the power of minus 3 mm. Nanometer. 1 nanometer is equals to 10 to the power of minus 9 m. Multiple units of meter. For the measurement of large lengths or distances, meter is considered as too small a unit. The most commonly used multiple unit of meter is kilometer. 1 kilometer is 1000 times a meter. 1 kilometer is equals to 1000 meters or 10 to the power of 3 m. Non-metric units of length. Bigger units. For the measurement of distance between two heavenly bodies, kilometer is considered too small a unit. The commonly used units for this purpose are astronomical units, which is denoted by AU, which means distance between Earth and Sun. Light year, which is denoted by LY, distance traveled by light in vacuum in 1 year. Parsec, distance from where semi-major axis of orbit of Earth, that is 1 AU, subtends at an angle of 1 second. Smaller units. To express the wavelength of light, size and separation between two molecules or atoms, radius of orbit of electron, etc., a small size of unit called angstrom is used, while the size of nucleus is expressed by still smaller unit called Fermi. Angstrom, it is the 10 to the power of minus 10th part of a meter. Fermi, it is a 10 to the power of minus 15th part of the meter. Let's see the table for smaller and bigger units of length. Units of mass. The SI units of mass is kilogram or kg. Mass of 1 liter is equals to 1000 ml of water at 4 degrees Celsius and is taken as 1 kilogram. In 1889, 1 kilogram was defined as the mass of cylindrical piece of platinum iridium alloy kept at International Bureau of Weights and Measures at Sèvres near Paris. Subunits of kilogram. For measurement of small masses, kilogram or kg is bigger unit of mass. The smaller unit of mass is common are gram and milligram. Gram is 1000 part of kilogram and milligram is equals to 1 millionth part of kilogram or its 1000 part of a gram. Multiple units of kilogram. The bigger common units of mass used in daily life are quintal and metric tons. Quintal is 100 times a kilogram. That is 1 quintal is 100 kgs. Metric ton, it is 1000 times a kilogram. 1 metric ton is equals to 1000 kgs, which is equals to 10 quintals. Non-metric unit of mass. The mass of atomic particles such as proton, neutron and electron is expressed in a unit called the atomic mass unit, symbol AMU, or unified atomic mass unit, symbol U. It is defined as below. 1 AMU or U is 1/12th mass of 1 carbon, that is 12th atom. The mass of large heavenly bodies is measured in terms of solar mass, where 1 solar mass is mass of the sun. That is 1 solar mass is equals to 2 into 10 to the power of 30 kgs. The commonly used smaller and bigger units of mass are summarized in the following table. Let's see the smaller and bigger units of mass in this table. Units of time. The SI unit of time is second, which is denoted by letter S. A second is defined as 1 by 86,400 part of a mean solar day. That is 1 second is equals to 1 by 86,400 into 1 mean solar day. For many years, the above definition of second remained in use. In 1964, a second was defined in the terms of energy change in cesium atom as follows. Let's see smaller units of time. The common smaller units of time are millisecond, ms, and microsecond, µs, shake and nanosecond, ns, where 1 ms is equals to 10 to the power of minus 3 s, and 1 mu s is equals to 10 to the power of minus 6s. 1 shake is equals to 10 to the power of minus 8s, and 1 ns is equals to 10 to the power of minus 9s. Bigger units of time. Sometimes second is smaller unit of time, and so we use other units of time such as minute, hour, day, lunar month, year, leap year, decade, century, and millennium. They are defined as follows. Minute. 1 minute is the duration of 60 seconds. That is, 1 minute is equals to 60 seconds. Hour. 1 hour is the duration of 60 minutes. That is, 1 hour is equals to 60 minutes. 60 into 60, where we get 3600 seconds. Day. The time taken by Earth to rotate once on its own axis is called a day. 1 day is divided in 24 hours. 1 day is equals to 24 into 60 minutes, which gives 1440 minutes. And in seconds, it would be 86,400 seconds. Let's see the lunar month. The Western or Gregorian calendar is based on period of revolution of the earth around the sun. But our Hindu, Vikram and Shak and Muslim Hijri calendars are based on the phases of moon as seen from the earth. In these calendars, 1 month is the time of 1 lunar cycle, which is nearly 29.5 days. The period of 12 lunar months thus comes out to be 354.37 days. Thus, 1 year of these lunar calendar is short nearly by 10 days of Gregorian calendar. Month. The Western or Gregorian calendar has January, March, May, July, August, October, and December each of 31 days, April, June, September, and November each of 30 days, and February of 28 days or 29 days in a leap year. To an approximation, a month is considered to be of 30 days and a year of 12 months or of 365 days. Year. 1 year is defined as the time in which the earth completes 1 revolution around the sun. The period of revolution of earth around the sun is nearly 365.256 days. To an approximation. Leap year. A leap year is a year in which the month of February is 29 days. That is, 1 leap year is equals to 366 days. Since the exact period of revolution of earth around the sun is 365.2422 days, therefore, to compensate for the excess of 0.2422 days in a year, the Gregorian calendar has been modified as follows. Every 4th year, that is year divisible by 4, has 1 day extra in the month of February, that is February 29. So that will be a leap year. For example, the years like 2000, 2004, 2008, 2012, 2016 were leap years. 2020, 2024 will also be leap years. The century years, that is 1800, 1900, though divisible by 4, are not leap years. Example, the year 2100 will not be a leap year, but the year which are divisible by 400 will be leap years, which will be year 2000, a leap year, and year 2400 will also be leap years. Decade. A decade is of 10 years. Thus, 1 decade is equals to 10 years, which is equals to 3.156 into 10 to the power of 8 seconds. Century. A century is of 100 years. In a century, there will be 24 years, each of 366 days, and 76 years, each of 365 days. Thus, 1 century is equals to 100 years, which can be calculated as follows. 24 into 366 plus 76 into 365 days. Millennium. A millennium is of 1000 years. That is, 1 millennium is equals to 3.16 into 10 to the power of 10 seconds. The commonly used bigger units of time are summarized in the following table. Bigger units of time. Derived units of some physical quantities. In the table below, we can see the definition, derived units, and abbreviations of some quantities. In this slide, we can see the continuation of derived units of some physical quantities. Guidelines for writing the units. Conventionally, the following rules are observed while writing the unit of physical quantity. The symbol for a unit which is not named after a scientist is written in small letters. For example, symbol for meter is M, and for second is S, and for kilogram it is kg, and so on. The symbol for a unit which is named after scientist is written with first letter of his name in capital. For example, capital N for Newton, capital J for Joule, capital W for Watt, PA for Pascal, HZ for Hertz, C for Coulomb, and V for Volt. Exception here is although later the unit of volume is not named after scientists, sometimes its symbol is written as L instead of small l. The full name of unit, irrespective of the fact whether it is named after a scientist or not, is always written with lower initial. Example, unit for mass is written as kilogram and not as capital K in kilogram. Unit of length is written as meter and not as capital M as in meter. A compound unit formed by multiplication of two or more units is written after putting a dot, cross, or leaving a space between two symbols. For example, the unit of torque is written as capital N dot M or capital N into M or Nm. Negative power is used for compound units, which are formed by dividing one unit by other. A unit in its short form is never written in plural. And to avoid powers of 10 in magnitude of quantity, prefix can be used with its unit, but a unit must not be written with more than one prefix. For example, instead of kmw, we must write gw. When prefix is used with the symbol of unit, the prefix and symbol combined becomes the new symbol of unit. For example, km cube means 10 to the power of 3 m whole to the power of cube is equals to 10 to the power of 9 m cube. It does not mean 10 to the power of 3 m to the power of 3.